Hi, everybody. Last class, we introduced the idea of ecological modeling that it extends basic population dynamics models by explicitly accounting for resources in the environment and the flow of resources from the environment into populations of organisms and from populations of organisms back into the environment. Today, we're going to expand upon those ideas a little bit, implementing a simple ecological model, playing around with it a little bit mathematically, seeing what simulation results from MATLAB give from this to get a little bit of insight into the type of things we can learn from this sort of model. Let me begin by sharing some slides on this. Go. All right. Now, we start off with a very simple model system, one where we might think of tracking only nitrogen as a single resource to consider from the environment. And we represent that with an environmental component. We have three different members of this ecosystem: a set of producers, so that is plants, that harvest energy from the sun and carbon dioxide from the atmosphere and water from the environment. We approximate these as being non-limiting, take nitrogen from the environment and grow and transform that into plant biomass. We have a set of primary consumers, herbivores, animals that eat the plants, transferring biomass from state P to state Z1. And then we also have a set of secondary consumers, carnivores, predators, organisms that consume the primary consumers. And again, biomass is transferred in that process. To simplify our model, we are going to assume that there's 100% efficiency in transfer. That is, when plants grow, they perfectly remove nitrogen from the environment, and all of the nitrogen they remove ends up in the plant biomass. When primary consumers eat the plants, all of the nitrogen is transferred into the next component, and so on. We have decay in our model. That is, that we have return of biomass from each of the organisms back into the environment, but we ignore any time lag in that. That is, as soon as we decrease the population of producers, that the biomass of producers, that available nitrogen immediately returns to the environment. Now, obviously, there's some limitations in this model, that nitrogen isn't the only resource, that there might not be 100% efficiency in transfer, that there absolutely is a decay a time lag in the decay process, returning things to the environment, but it's a starting point. So given this model, we can write down a system of equations shown here, largely the same as what we outlined in class the other day. Right? What we've done here is I've created a set of 4 differential equations, one for each component in the system: the environmental nitrogen, the producer, the nitrogen in primary consumers, the nitrogen in secondary consumers. And remember that our units here are being tracked in something like mass of nitrogen. That this is one way of describing the population of plants, the population of primary consumers, the population of secondary consumers, is simply by asking how much biomass they have and measuring that only in terms of the nitrogen component. For each of these, we have a term that describes how the value grows and terms that describe how those values decrease. The growth terms for all of the living components are bilinear models where the growth depends on the population of the growing entity, right? So the plant growth depends on plants, herbivore growth depends on herbivore population, secondary consumer growth depends on secondary consumer population. This makes sense for biological growth, since growth comes from a parent. But the growth also depends on the resource that these organisms need to grow. Plants require nitrogen, herbivores require plants, carnivores require herbivores, and so we have these bilinear growth terms. Each of these growth terms, because they represent a transfer of nitrogen from one component to the next, all also show up in the model as negative terms for the lower level in the hierarchy of consumption. So plant growth ends up as a negative in environmental nitrogen. Herbivore growth shows up as a negative for plant biomass, and secondary consumer growth ends up as a negative for primary consumer nitrogen. So that covers part of the growth term for 3 of the 4 equations, and one of the decay terms for 3 of them. We also have another decay term for each of the animal, for the living organism populations, a death or decay, loss of biomass term that depends only linearly on its source population. So we have plant decay, herbivore decay, and secondary consumer decay here. Because these decay terms all represent, in some sense, death of the organism or loss of biomass through other means, they all correspond to a positive in the environmental nitrogen component. All right. So this is our model. What do we learn from this? What can we learn from this? Well, one of the things that we can look at is we can ask, what are some of the ways this system behaves, the requirements of this system? Is there a requirement on total nitrogen, and so on, under different conditions? And to simplify things, I'd like to start with a plants-only system. That is, what if this larger model can be reduced down to a system with only plants and an environment by setting Z1 and Z2 equal to 0. That makes these last 2 differential equations really just disappear. It makes this last term of the plant equation, apologies, disappear. And it makes the second 2 growth terms in the environment disappear. Right. We then can ask, what do we learn from this? Well, the result has actually only 2 differential equations with 2 terms. one that's bilinear in N and P and one that depends only on P. And the dp dt and dn dt will be related by a simple negative because there's just a flow between two compartments. In steady state, these two have to be equal. And in such a steady state, that means that the plant growth term has to exactly equal the plant decay term. And this can only happen under two conditions. One, P is 0. This is the case where there is no plant life at all. There is no life. This is an environment that only has nitrogen in the environment and nothing growing, something of a boring case. If plant biomass is not equal to 0, then we can cross off these terms and we have gamma n equals alpha, or n equals alpha over gamma. Plants, of course, then would be the total amount of nitrogen in the system minus the amount that's in this in the environment to give an expression for the nitrogen in plants as n naught minus alpha over gamma. Now, interestingly, what this says is that once plant life is present, the environmental nitrogen levels will be a constant that's set by the plant growth and decay rates and is independent of total nitrogen. That level in the environment will always be alpha over gamma. Plants cannot exist stably. They will go extinct if the total nitrogens do not meet this level. And so if you think about an environment that has maybe some seed base, some potential for growing plants, and you add nitrogen into the system, as long as the nitrogen levels are below alpha over gamma, we do not expect there to be a stable population of plants. But as soon as those total nitrogen levels exceed this, then plants can stably persist. And if we increase the amount of nitrogen in the environment above that boundary, all of that excess nitrogen goes into extra plant growth. Right? The environmental levels stay at this threshold level. That's we can see this in a simulation of the system, right? As shown here. This is just the output from a MATLAB simulation of a plants-only system where we've set the growth rates of the plants and animals to 0 so that they can't persist in the herbivores and carnivores to 0 so they can't persist in the system. We've set alpha to have and gamma to have these values where alpha is twice that of gamma. So we have an alpha over gamma of 2. And as we start off with a total nitrogen of 12 and almost no plants. We can't start off with exactly 0. We have to start with a tiny fraction. And when we do that, we see that the simulation, this is actually a simulation over a 20-year time scale, within the first year or so, given these parameters, the plant population increases to some maximal value, while the environmental population decreases down to this threshold. And we see then we level off at a threshold of 2 for environmental nitrogen, and all of the rest goes into plants. Now, what we notice here is that this curve looks something like logistic growth. It looks like the limited growth. We start off with exponential growth, but it maxes out. And this is happening even though we don't have a logistic growth model in the system. We have a simple bilinear growth model, but it's the fact that we have a limit of nitrogen in the system that causes this. So rather than implicitly capping the population with, say, some carrying capacity, we explicitly limit the population through this limiting resource, right? So that's plants only. Now let's add herbivores into the system. And we will begin by looking at the math of it. Here, Z2 is the only one that is 0. This lets us ignore the last equation of the system, and it lets us ignore the decay term for the carnivores, and the loss of herbivore population from predation. We then have the fact that we lose this last term on the herbivore population gives us quite a simple remaining equation for the dynamics of the herbivores, right? dz1 dt is d delta 1 p z1 minus beta 1 z1. For this to be equal to 0 in steady state, these two terms have to be equal to one another. So we get delta 1 p z1 equals beta 1 z1. This can only be true either if z1 is 0, there are no herbivores, it's a plant-only system, which we've already discussed. Or if herbivores are present, then delta p1 has to be equal to beta 1, so p has to be beta 1 over delta 1. Interestingly, we see again a population, this time the population of plants, or the amount of nitrogen in plants, is a simple constant that is set by a ratio of rates, in this case the herbivore growth and decay rates, and it's the plant biomass that is unchanging with response to or independent of nitrogen level in this steady state. The remaining two pieces are a little bit more involved. The plant population, in order to be at equilibrium, has to satisfy this equation here, but there's a p in every term. So since p is not, if we're going to consider the p not equal 0 case, that is p set by this value, we can cancel those terms out. And what we're left with is that the growth term of gamma n has to equal the sum of the decay terms, alpha, sorry, and this should be a plus here. Let me, I'll fix this typo before I show it up. I'll show it upload them to Brightspace. And we can rearrange this by dividing through by gamma, and we have the nitrogen levels are alpha over gamma. This is the same value that we saw in the plants only case, plus gamma over, so delta 1 over gamma times z1. And so what we see is that the plant population is constant, or so the plant biomass is constant. The environmental nitrogen is that same threshold level that was required to support plants, plus a term that is dependent on the animal population, the herbivore population, but scaled by a couple other parameters. The animal population, we can actually find an expression for by noting that the total nitrogen population minus the environmental in plants, everything else has to be in herbivores, and doing some rearrangements that I don't want to go through the work of, substituting in beta 1, delta 1 for p, substituting in this expression for n, gives us an expression that only depends on z1, and some rearrangements give us this form here. Right? Once again, we see that, and of course, this term also depends on total nitrogen. Once again, we see that herbivores can only stably persist if there's a certain level of nitrogen available. We can see what that has to be in two ways. First of all, looking at the animal population, if the sum of these two terms is less than n naught, we would get a negative population, which doesn't make sense. And so clearly the sum of these two terms, alpha over gamma plus beta 1 over delta 1, has to be greater than n naught to support a herbivore population. We also can get the same result from a sort of a slightly different angle. We can see that at equilibrium, the amount of nitrogen in plants has to be this value, the second piece of this. And the amount of nitrogen in the environment has to be this constant, this sort of threshold value that we saw before, plus a little bit. This value can't be negative since it depends on the animal population. So the lowest possible combination of these two is the sum of these two terms, which is exactly what we have. Right? So once again, we have a part of the system is independent of total nitrogen. When we add extra nitrogen, we have to have a certain threshold of nitrogen to support a herbivore population. Once we have that, excess nitrogen goes into two places. Some of it goes into supporting a larger herbivore population, and some of it returns to the environment. Plant population is independent of this excess nitrogen. So as we did in the last case, we can ask, what does this look like now when we do a simulation of a system like this? And this is what we see here. We have now added into our model. We're still actually starting at exactly the same place. Alpha and gamma exactly the same as before. Nitrogen value, total nitrogen the same as before, but now we've added in herbivore growth. The parameters here are slower by a factor of 2 than the plant growth parameters. So the animal growth will be slower than plant growth in some sort of general sense, but chosen such that the total plant biomass set by the ratio of these terms will be 2. If we plug in these values into the equations we saw before, we find that the environmental nitrogen mass at equilibrium should be 14 over 3, or 4 2/3, and the herbivore biomass should be 16 over 3, or 5 1/3. So what do we see when we start off our simulation? Again, with everything in all the nitrogen in the environment, except for tiny, tiny starter populations of plants and animals. We see that, as we saw before, in the first year or so, there's a rapid drop-off in the environmental nitrogen, growth of plants, almost reaching that threshold level of 10 for plants and 2 for environment. But then, as the plant population grows, it starts to be able to support herbivore population. And so we see, with a bit of a lag, partly coming just from the fact that you need plants before the animals can grow, and partly coming from the slower growth, we start to see the herbivore population increase. As the herbivore population increases, the plant population decreases. We also see, as this happens, there starts to be an increase in the amount of nitrogen in the environment. There's a little bit of wiggling before things settle down, but in the end, we settle at exactly the values that we'd like. We expected stable population of plants, much, much lower than the plant population would be in absence of herbivores. Biomass of only 2 for plants, rather than the herbivore free of 10. A large herbivore population at a little bit over 5, and an environmental nitrogen content a little bit over 4. All as expected. Now, you might expect what we're going to do next. Add in the secondary consumers into this. Now, as we do this, the math gets a little bit more messy because now we have all four of these equations that we have to consider. I'm not going to dig into this too much. If you want to play around with it on paper, you can, but let me highlight the key results. We start with the last equation. Because it's the simplest, it only has two terms here. Okay? At equilibrium, these two terms need to equal one another. So delta 2 z1 z2 has to equal beta 2 z2. This can be true if z2 is 0. That is, there's no predator population. There's only plants and herbivores. So we've already considered that, so we won't worry about that case any longer. If z2 isn't equal to 0, then we can cancel it out on either sides, and we have delta 2 z1 has to equal beta 2, or z1 has to equal beta 2 over delta 2. Once again, we have this same result that we saw before, that one of the biomass components is independent of total nitrogen and is a simple ratio of two rates. In this case, it's the herbivore population that is fixed. When there were only plants, it was the environmental nitrogen. When there was only herbivores, it was the plant population. When we have a secondary consumer population, it's the herbivore population that is fixed in this way. Okay? Once we have a value for z1, then this third equation becomes a little bit easier because we can substitute z1 into it. The plant equation also becomes a little bit easier because we can substitute z1 into it. Let's actually jump down to the plant equation because it turns out that the math is just a little bit easier to work with in this case. In the plant equation, equilibrium requires that this growth term balances the decay term. All of these have a p in them. So if p is 0, this would be satisfied, but we know we don't want a population with no plants or an ecosystem with no plants. So the alternative is that the growth piece of gamma n has to equal the decay terms of alpha plus delta 1 z1. Z1, of course, we know what the value has to be at equilibrium, so we plug this in and we get a final relationship that nitrogen has to be alpha over gamma. This is that same term that we saw before, minus delta 1 over gamma times this ratio, beta 1 delta 2, sorry, beta 2 over delta 2. Now, of course, this is just z1. This is actually the same expression that we got for total nitrogen before, right? The threshold requirement of alpha over gamma plus a scaled version of the herbivore population. But in this case, the herbivore population is constant, independent of total nitrogen, which means that the free nitrogen, the environmental nitrogen, also is just a constant, independent of the total nitrogen levels. We then can go on to the third equation now, recognizing, first of all, that all of the terms have a z1. Z1, of course, could be 0, but that would be the system with no animals. And so, oops, apologies on that. Nope. If the herbivore population is not 0, then growth delta 1p needs to equal the decay terms beta 1 plus delta 2 Z2, and we can rearrange this expression to give a plant population that's a ratio of beta 1 delta 1. This was the same constant plant population that we saw in the presence of herbivores, but with no carnivore, plus a scaled version of the carnivore population, analogous to what we saw in the previous case for free nitrogen. I haven't written this down, but of course we can, if we know Z1 and N, just in terms of the parameters, and P in terms of Z2, we could write Z2, an expression that now factors in the total nitrogen and find an expression for Z2. I don't want to go through the algebra of that here. Plant population will vary depending on total nitrogen, however, because excess total nitrogen will go into carnivore growth and increase in the plant population based on this term here. What's the minimum total nitrogen to require to support a secondary consumer population? Well, we need to have enough to have this constant herbivore population. So we have that term. We have to have enough in the environment, which is this sort of sum of terms here. The threshold value plus this scaled amount of the herbivore population. So we have these terms here. And the plant population has a constant piece, this thresholding term, plus an excess bit that depends on the the carnivore population. And so this piece is also a minimum. Right? And altogether, we have an expression for the minimal total nitrogen, which is really a little bit more than what we needed to support just the herbivore population. All right, so as we did last time, let's take a look at how this looks in a simulation. Same total nitrogen, same parameters for plants, same parameters for herbivores. We've now added in a secondary consumer piece. And we've chosen the growth rates here such that the ratio beta 1 delta 2 will give us 4. And just because of coincidence of our choice of parameters, all being sort of simple factors of 2, this remember alpha over gamma was a 2. Beta over delta 2 is 4, but delta 1 over gamma would be half. And so this sum happens to also give us the same value. We won't always get the same herbivore and environmental nitrogen value, but we do in this case. Starting off at a system that's almost all environmental nitrogen, we initially get decay of environmental nitrogen as plants grow, as we saw before. They almost reach the threshold values, and then our herbivore population starts to grow. As the herbivore population starts to grow, the plant population decreases and the environmental nitrogen population increases. There's a few wiggles. They start to close to level off to what we saw earlier with a close to 2 plant population, and herbivore and environmental plant nitrogen levels close to the equilibrium levels before, but not exactly, because as this starts to happen, we start getting growth of the secondary population, the secondary consumer population, the carnivore population, and that this relatively modest growth amount of biomass going into the carnivore population has a larger impact on the herbivore population. As the herbivore population decreases, the plant population increases. Environmental levels drop a little bit, and finally they settle down at the equilibrium we would expect. Environment and herbivore populations both at exactly 4, as the two equations give us. A relatively small amount of biomass in the carnivore population, and a larger amount in the plants. All right. So really one of the big take-home lessons here is that we see that the total nitrogen level in the system dictates the number of trophic levels that are allowed. That if we have less than some threshold value of alpha over gamma in the environment, we can't even have plants stably grown. As we sort of raise those levels, we pass a threshold and we're able to support a plant population. Once we do that, we start to feed that extra levels into an herbivore population, into the plant population. Once the total nitrogen levels hit some larger value, the threshold plus this extra bit, we can then start supporting herbivores as well, primary consumers. Once we're in that state, the excess nitrogen drives growth of the herbivore population, plants level off, and at some larger threshold value, the same threshold value for plants, plus the same threshold value for herbivores, but plus an additional requirement that depends on the predator populations or the predator growth and decay rates. A higher threshold is required to support a predator population. So we can see this visually by taking the same full model that we described, where we haven't zeroed out intentionally the predator or herbivore population, that all of the pieces are in the puzzle. But we start with our full model and we start asking what happens if we look at exactly the same thing, but with decreasing levels of nitrogen. This is what we just saw before, our base model, total nitrogen levels of 12. This is above the threshold needed to support a secondary consumer population. That threshold was 10. And we got an equilibrium that had a balanced, a level herbivore population, a small carnivore population, and so on. As we now decrease and we take the population to 10, right? This is now right at this threshold value. Because we're right at this threshold value, we cannot support an herbivore, a carnivore population. The secondary consumer population is at 0. It never grows. Right? We're still at that same threshold level, though. We have that balanced herbivore and environmental population, and we have also our plant level right at that threshold level that we expected it to stay static at in an herbivore population alone. Right? As we decrease even more, down to 8, now we're below this threshold, so we know that we can't support a secondary consumer population, as we see here. we're well above the threshold for herbivores. And so now we see that our plant population stays at this level value of 2, this constant value we expect. And as we decrease compared to 10, we see that when we had 10, we had both the environment and the herbivore population at 4. Plants were fixed at 2. Now, both of those decrease. Plants remain at 2, but the herbivore and environmental levels decrease a bit. Going down to 6, still above this level, we see this process continue. Plant population still remains at 2. Environmental populations have decreased a little bit more. Herbivore populations have decreased even more, down to just a little bit over 1. And if we now go down one more step to where we're sitting at the threshold value, we still see that plants sit at 2. And now the nitrogen levels have matched that, have hit exactly that thresholding behavior of alpha over gamma. Or that stable level of alpha over gamma in a plant-only situation. And herbivore populations are down to 0. We take one more step, a little bit more. Now we're above the requirement to maintain plants, but below the requirement to maintain herbivores. Herbivore population, of course, is 0. Now our nitrogen levels, or environmental nitrogen levels, stay at that alpha over gamma. They don't change. We only have a little bit of excess, and that little bit of excess goes into the plant population here. If we take a last step down to a population, a total nitrogen of only 2, this is now right at this thresholding level, which means we're equal to this. We're not above it, which means we can't support a plant population. The plant population never grows. We start in this situation, and the environmental levels just stay at that level. All environment in nitrogen stays in the environment. There is no ecosystem. Right? And of course, if we had even lower values, we would just see flat lines for the environmental concentration below this. So where do we end up at the end of this? We've sort of introduced this simple model, and even though it's really quite simplistic, that we just have simple bilinear growth, we have simple linear decay, we only have 4 levels, we only are tracking nitrogen, we already see some interesting results. We see that we can define a minimum total nitrogen level to support each trophic level, a certain level to support plants, a larger level to support herbivores, even larger level to also support carnivores. The environment needs to be richer in some sense, has to have more overall resources in order to be able to support more trophic levels. Right? One of the very interesting things is that once we're at the level required to support one of these things, to support plants and herbivores, plants, herbivores, and carnivores, for example, the penultimate trophic level, that is the level 1 below the top, always has a constant population size that doesn't depend on the excess nitrogen. Right? That is that the excess nitrogen, once we're above this threshold, largely goes into feeding the added layer, the added trophic level, does not impact growth at the next level down, and then also has a bleed through effect on the lower level. Right? And this is, I think, quite an interesting result. It's a result that you could imagine trying to test experimentally and ask, in an idealized ecosystem, is this the sort of behavior that we see? Right? Now, will it match? Perhaps it will, perhaps it won't. This is a very simplistic model. There are conditions under which we would expect this model to behave quite well. One of the key things in this is that nitrogen is it has to be the only limiting factor. We need to have excess energy, oxygen, carbon dioxide, water, and so on. We need to have unlimited nesting sites for the animal populations and so on. And so everything else needs to be in excess compared to the population sizes we see. But despite some of the limitations of this, we still are able to get interesting insights. And the framework that we've started with here is able to be extended to larger and larger systems. We can, once we have this basic starting piece, we can imagine adding additional trophic levels, adding multiple herbivores that compete against one another, multiple predator species that compete against one another, and perhaps additional resources. All right. Now, ecological modeling is itself a huge field. There's you could spend an entire career exploring all of these different options. My goal in this lesson and the last class was really to just give a very slight feeling for how these sorts of models work and the sorts of things that we can learn from them. Right. Thank you.